Hello and welcome to 2.4 Forces of Friction. So we're going to take our two-dimensional force problems and we're going to extend them now to problems that have friction in them. If you remember, there are two types of friction. Kinetic friction, which is when an object is moving, and the formula for this, for kinetic friction, is Fk equals mu k Fn. And if that symbol mu is new for you, this is the Greek letter mu. It looks sort of like a U, but with an extra stem on the front of it. And it's the Greek letter mu, like this, mu. Okay, and you might recognize it from torrenting. If you've ever used microtorrent, it has the same symbol. So that's the symbol we're talking about here. So mu k is the coefficient of kinetic friction and that just means that you can see from our formula Fk is mu k Fn, so it means that as the normal force increases, so does the kinetic friction, and it increases at this proportion called mu k. And that mu value is going to be unique for any pair of surfaces. So if I have steel on ice, that has a certain coefficient, and a different pair of things like wood on carpet would have a different coefficient of friction. Okay, so static friction is when an object isn't moving, and our formula here is Fs max, so the maximum static friction is equal to mu s Fn. Remember that with static friction, there's sort of a range of static friction values. It's just stopping something from moving until you exceed the maximum static friction, in which case it starts moving. Okay, and mu s, of course, is the, well, it's the same thing as above, but for static friction. Alright, and to get your values of mu for the different coefficients of friction, we use a table of friction values, like the one on page 85. So if I know I have steel on ice, I go to my table on page 85, and I can look up the coefficient of friction there. But on tests, you'll either be given a table, or you will have the coefficients told to you in the problem, like in this problem below here, where it tells us the coefficient. So we'll look at this problem. It says a worker must move a crate that can be either pushed or pulled, as shown to the right. The worker can exert a force of 3.6 times 10 to the 2 newtons, and the crate has a mass of 45 kilograms. The worker can push or pull the crate at an angle of 25 degrees, and the coefficient of kinetic friction between the floor and the crate is 0.36. And we want to first find the acceleration when pushing the crate. So what we're doing here, we have this crate, and I'm pushing it forward at an angle. So you can see that I'm pushing forwards, but I'm also pushing down a bit into the ground. Whereas the other problem, I'm pulling it up, so it means I'm pulling it forwards and lifting it up a bit. So we'll see how those two problems are different. So first it says, pushing the crate, let's find our acceleration. We start with a free body diagram. So I'll draw my box here, and we've got gravity down, normal force up, kinetic friction backwards because we're moving, and the action force is acting downwards. And I can say that it's 25 degrees from the horizontal. So you can see that's going to make a little triangle here. Now, I can make a few statements. I can say that the net y force is equal to 0. That's because it's not falling into the ground. It's being held up on the ground. So this tells me that my normal force upwards has to be equal to all the downwards forces. So mg plus Fa sine 25 degrees. And I can find the value now for normal force because I have all those values. So I have 45 times 9.8 plus my action force, 3.6 times 10 to the 2, sine 25 degrees. And this gives me a value of 593.14 newtons. Good. Now I can also make a statement about my net X force. I can say that the net X force is equal to, well, all the ones to the right. So we've got here Fa cosine 25 degrees. And then all the forces to the left, so minus Fk. And I can plug in some values for this here, so I have 3.6 times 10 to the 2 cosine 25 degrees minus my kinetic friction. Well, I'm just going to write up here Fa cos 25 degrees minus, I'm just going to expand this a bit. So Fk was mu k Fn. Okay. So now I can say, I have my Fa cos 25 degrees, now I can say minus mu k, so 0.36, times my normal force, and I calculated that up here, 593.14. And this tells me that my net X force is going to be 112.74 newtons. And I'm sorry, I didn't leave us a lot of space for this problem, so I'm sort of crowding things in here a bit. But there we go, we have our net X force, and now I can say the net force is equal to ma. So A is equal to net force over m. Our net force is just the X force because y is all cancelled out. So here I can say that it's equal to 112.74 divided by my mass, which was 45 kilograms. And this gives me a value of 2.5 meters per second squared. There's my final answer. Okay, we're going to do the exact same thing for the problem below. So I'll draw all my forces. mg hasn't changed. Fn is right here. Still have kinetic friction. And we have our action force now upwards at the same angle. Alright, and I can do the same thing here. So I can say that my normal force, again, I can say net y force is equal to 0, which means that Fn is equal to mg minus. Now, before we had plus the vertical component of the action force. Now it's going to be minus that because the action force is acting in the same direction as the normal. So minus Fa sine 25 degrees. And I plug in my numbers here, 45, 9.8, minus 3.6 times 10 to the 2 sine 25 degrees. This gives me a normal force of 288.86 newtons. Notice that that is considerably less than it was above. Okay, now we can proceed. We can say that the net X force is equal to, well, we still have in the positive direction, we have Fa cosine 25 degrees. And still in the negative, we have minus Fk. Okay, and I can rewrite this again, Fa cosine 25 degrees minus mu k Fn. And now I need to fill in some numbers here. So I can say that this is 3.6 times 10 to the 2 cosine 25 minus, and my mu k was 0.36. My new normal force is 288.86. So this gives me a net X force of 103.99 newtons. Good. Now we can make the same statement that we made above. Net force equals ma, rearranged for acceleration. Net force over m. And this is going to be now 103.99 divided by 45, which gives me well, I'm sorry, I think that I've done something wrong here. I'm sorry, I did do something wrong. 103.99 was not correct. 103.99 is just the value of the kinetic friction. So I'll erase that guy here. And I have to erase this here. Okay, if you're following along, I'm sorry. Here we go, 222.28 newtons. That is our net X force. Okay. So now I can write this 222.28 over 45, and this gives me 4.9 meters per second squared. Perfect. So that's it. We have two accelerations. You can see that the second one is almost twice as much acceleration. Which is faster or are both the same? Well, turns out pulling is the same. Or sorry, pulling is faster. More acceleration. And just thinking about that, does that make sense? Well, when I'm pulling, I'm also lifting it up a bit this way, which means I'm reducing the normal force and reducing friction. So I'm actually pulling it off the ground a bit, which is going to make it slide faster. So yeah, that makes sense. Pulling is actually going to be better than pushing, where I'm actually pushing it down and I'm giving it even more normal force for more friction. Good. Number 2, or page 2 here, we're going to look at a few more problems. So this says a crate is placed on an inclined board as shown to the right. One end of the board is hinged so that the angle theta is adjustable. The coefficient of static friction between the crate and the board is 0.3, and to determine the angle at which the crate just begins to slip. I really like this problem. I think it's really cool because, look, the only piece of information we're given here is the coefficient. That's the only information. We don't know the mass. We don't know, well, I mean, the mass is the main thing that we're interested in here, and we don't know it. So I will draw a free body diagram. And let's see, I have, if the surface is on that incline that we see over there, that means the normal force is going to be up in this direction. And static friction is keeping it from sliding down. So static friction is going back in this direction. Meanwhile, gravity is straight down. Now remember, for these sorts of problems, it makes our lives a lot easier if I define x and y relative to the direction of motion. So here I'm going to say that this is x and this direction is y. So now I can break this guy up. I can break my gravity up into those components there. And now the question is, what is this angle theta? And notice that that theta matches this theta because of similar triangles. And if you don't see why that is, please ask me in class and we can look at it together. But yeah, we have theta there, so now I can solve this problem. Well, we'll see how. So the normal force and this piece of gravity have to cancel out because the net force in that dimension is 0. It's not going into the surface here. So we can say that those two pieces have to be equal. Fn equals mg cosine theta. And so this is sort of the y component of gravity. Good. And now in the other direction, the x component of gravity, I can say that the static friction we're saying that it just starts to slip. So we're saying this is just where everything's balanced. So the static friction is equal to mu s. Well, we're saying that the static friction and gravity have to be balanced here. So we're going to say mg is equal to mg sine theta. So this is the x gravity. Now, the other thing we can say is that Fs is equal to mu s Fn. And we just said above that Fn is equal to mg cosine theta. So then what we can say is that we have this statement for Fs and this statement for Fs. Those are equal to each other, so I can use those now, and I can say that mg sine theta is equal to mu s mg cosine theta. And look how nice this is, because our mg's just cross out. Now I have sine theta is equal to mu s cos theta. Sine theta is equal to mu s cosine theta. And now we don't need to know mass. I can solve this here. I can say that mu s, I'll put this over here, mu s is equal to sine theta over cosine theta, and sine over cosine, well, that's just equal to tan. So this is tan theta. Now I can say that tan theta is equal to mu s, so we can say that theta is equal to the tan inverse of mu s, which is equal to tan inverse of 0.3, and there we get 17 degrees. There we go. We solved it without knowing the mass. And so that's really cool. It means that this sort of situation, which is a very plausible real-world situation, if you want to know sort of what the maximum angle is before something starts sliding, all you need is mu s. Here's our equation. It's theta, the angle, is equal to the tan inverse of mu s. And I think that's pretty cool. Okay, so I'm just going to underline that because I think that's a pretty neat statement. All right, one last problem here. It says two blocks are joined with a rope that runs over a pulley. The mass of M2 is 5.0 kilograms and the incline is 35 degrees. The coefficient of static friction between M1 and the inclined plane is 0.25. Determine the largest mass for M1 such that both blocks may remain at rest. All right. Well, this is the same kind of idea for this problem. And it's all sort of fun, tricky stuff. So, let's just look at this here. I can make my free body diagram for mass 1. I can say that mass 1 has tension acting upwards. And I can say that it has the normal force going this way. And it has gravity going this way, m1g. And what else? We have static friction somewhere. And so the static friction could be acting down this way or it could be acting up this way. Now we're saying the largest mass for M1 so that they both remain at rest. So what we're saying is I'm making M1 larger and larger and larger, heavier and heavier, so that it's almost about to start sliding down this way, but it's not. Right? And so that means my static friction is going to be going in the opposite direction from the way that it wants to move. You can see that the opposite of this question is if we said, what's the minimum mass of M1? Well, we're making M1 lighter and lighter and lighter, so that it wants to start going up this way, and then we'd have static friction acting in the opposite direction. So we could solve both of these problems, but here it's saying we want the largest mass of M1, so that means our static friction is going to be stopping M1 from sliding down to the left. So here's my static friction. All right, and there's my picture. Now I've got M2, gets its own picture here, and here we have Ft and M2g. And here Ft and M2g have to be balanced because this is all in equilibrium. So I'll do one last thing here, which is to say that I want to find I want to break up M1G into components. So the way I can do that here, I just break it into perpendicular components, and this angle in here is going to be 35 degrees. And that, again, is from similar triangles with this. Now what I'm doing to get those, I'm sort of drawing this whole situation out. I've got the box. I've sort of gone ahead and done this already, but I try to get my similar triangles from the principles of of the similar triangles. So if you're not understanding how we can decide that that's 35 degrees and how we know that it's that one and not this one that's 35 degrees, talk to me in class. We can look through that. Okay. So I can start making some statements. Ft is equal to m2g. We know that because this has to be in equilibrium. Good. This also needs to be in equilibrium, so we can make some good statements about that as well. So for instance, we can say on mass 1, we can say that the normal force is equal to m1g cosine 35 degrees. Right? That's to say that those forces in that dimension need to cancel out to 0. Okay. What else can we say? Well, we can say something about the other dimension for that one. So we can say Fs is equal to, so here we've got our, so the static force going up to the right has to be equal to m1g sine 35 degrees minus Ft, because that all needs to balance out. Okay, and the last thing we can say is we have the coefficient of friction here, so Fs is equal to 0.25 times Fn. So Fn, which is 0.25, and I take my value for Fn from above. m1g cosine 35 degrees. Okay, now I've got something to work with. I can start solving these problems here. So I have two statements for Fs. I can set them equal to each other. So here I can say that (0.25 m1g cosine 35 degrees is equal to the other statement for Fs. And I'm just going to expand this other statement one last bit here because we already have a value for Ft from above. So we'll use Ft from above. This gives us m1g sine 35 minus m2g. Okay, so now we can use that whole thing below here. m1g sine 35 degrees minus m2g. Alright, and now with a bit of creative rearranging, we can find the mass of m1. You can see that we can get two m1 terms on the left. I'll just do that here. We get 0.25 m1g cosine 35 minus m1g sine 35 degrees is equal to negative m2g. And now you can see that everything has a g on it as well, so we can cross those out. We can just get rid of g from this equation. Finally, we can get m1 is equal to negative m2 over 0.25 cosine 35 degrees minus sine 35 degrees. And this gives us 13.56 kilograms, which we round to 14 kilograms. Okay, There we go. There's our final answer. And notice, I mean, that's not maybe an intuitive answer. I mean, you know, there's no way you could have just guessed that. But if you follow step by step all the information that you're given, eventually you can get to an answer. And that's really what we're working at here. So there's a few problems there that we can do in class, and I'll see you in the next lesson.